couple of questions. So we've got function here. We know the derivative of f is given by this. So this is obviously cubic. The derivative is given by this expression here. If there's a minimum point at A, and we're trying to find the x-coordinate, just the x-coordinate, we know that this expression here must be equal to 0 at that point. So we want 3x squared minus 8x minus 3 equals 0. Let's try and factorize it. So we're going to multiply first and last number, so it's -9. So I want two numbers that multiply to give -9 and add to give -8. So that's 3x squared minus 9x plus x minus 3. Okay, so 3x is common. So we've got 3x plus 1, x minus 3. And that means our two values are -1. Oh, plus I should do some colour. -1/3 and 3. So they're the two times that there's a turning point. So obviously the x-coordinate of A is going to be x equals 3. You must make that statement because there's only one x-coordinate, and this is the x-coordinate for this point here. Alright, the y-intercept of the graph is at 0, 6. Find an expression for fx. Okay, so if this is f dash x, we can find fx by integrating. I'm just going to have to come down here. So the integral 3x squared minus 8x minus 3 dx is 3x cubed over 3 minus 8x squared over 2 minus 3x plus c. They cancel each other out, and 8 over 2 becomes 4. So we know it goes through the point 0, 6, and so f of 0 equals 6. So that means that 0 cubed minus 4 times 0 squared minus 3 times 0 plus c equals 6. So c is 6. So our equation for fx is x cubed minus 4x squared minus 3x plus 6. Okay, so we've got finding. Okay, the graph of function is by reflecting the graph in the y-axis, followed by a translation. Excuse me. Find the x-coordinate of the local minimum point on the graph G. Alright, so for reflection. Okay, we're reflecting it. This point is now going to come up here, and this point is now going to come down here, which makes this now the new minimum point. So we said this coordinate was -1/3 originally. And then we've got a translation of mn. So m is going to tell us the horizontal movement, n tells us the vertical. So it's going to be -1. Oh, sorry, to read the question. A reflection in the y-axis. Oh, duh. Forget that. Start again. So reflection in the y-axis means this here is going to now become over here at -3. And then, sorry, this bit is applied, so we've got a translation of mn, so we would have -3 plus m. They only want to know the x coordinate, so that would be -3 plus m. Okay. Okay, so LX family lines. Oh, I don't really like the way this is written. So this is obviously just two values. So we haven't got x, y, z. We've just got x and y. So if they want the equation of L1, we're just going to substitute the value of 1 in place of the x. So that's going to be r equals 1, and 2 over 1 is 2, plus 1 squared. So that's just going to be, oh, okay, so we should take that t there, minus 1. Oh, that's a minus. Okay. A line LA crosses the y-axis at point P, so that point P has coordinate 0 for A. Okay, so if we're, our equation would be R equals 0, no, what am I talking about? A 2 over A, oh god, sorry, plus T brackets A squared minus 2. Okay, and then our y coordinate is this second one here, so that means 2, oh god. Okay, that's going to be 2 over A minus 2t, and that equals 4 over, oh, show that it equals it, oh darn it. Okay, so we need to show it, so we've got 2 over A minus 2t, but now we need to find the value of t. Oh, we'll have space. So we know that the x coordinate is A, so we know that A plus A squared times t equals 0. So A equals A squared, sorry, negative A squared t. So t equals A over negative A squared. So t equals -1 over A. Now we're going to stick that in here. So we've got 2 over A minus 2 lots of -1 over A, which is 2 over A plus 2 over A, which is 4 over A. Sorry, it's a bit messy. Alright, a line LA crosses the x-axis at Q. Let D equals PQ squared, show that D equals, okay. Alright, so if we now know P and Q, and we're talking about PQ squared, so we're trying to find the vector from P to Q, so we know that's minus, so for position vectors we go the opposite of P, so that's -0, 4 over A, and then plus Q, so that's 2A, 0. So that would be 2A, and then minus 4 over A. Okay, so that's the vector P from P to Q, and then we're going to square that. Oh no, so D equals PQ squared. So we've got so that's it. So we can use Pythagoras' theorem, because we know that this. Let's just picture this. So we've got P, we've got Q, we've got the origin here. So we're going from P to Q. So we went the reverse along P. We went the positive direction on Q to initially get that. We now have this as a vector, so we can find PQ squared by taking this measurement here, this measurement here, which is our 2a and our negative 4 over a. So we've got 2a squared plus negative 4 over a squared, which is 4a squared plus 16 over a squared. Okay, so let's see. D, there's a minimum value for D. Find the value that gives the minimum value. So we know minimums occur when the derivatives are equal to 0. So minimum and D dash equals 0. So D dash is going to be 8a plus, maybe we need to rewrite this first. So that's 4a squared plus 16a to the negative 2. Okay, so going back to the derivative, so we've got 8a minus 32a to the negative 3. So we've got 8a minus 32 over a cubed equals 0 for the minimum. So 8a equals 32 over a cubed. A4 equals 32 over 8. So I've just brought the a cubed up here, and then I've moved the 8 across. So a to the 4 is 32 over 8, which is 4. Remember, if we're trying to fourth root it, we're square rooting it twice. So a squared would be 2. So a will be root 2. I think that's it.